Hi, today we're going to be continuing talking about equilibrium. And today we're going to be looking at the factors that affect chemical equilibrium. All right, we last talked about how since chemical equilibrium is the state in which you have a reversible reaction and one in which the forward reaction rate is equal to the reverse reaction's reaction rate. And since they're both happening at the same time, at the same speed, the reaction appears to have stopped. And you have a certain amount of products, you have a certain amount of reactants, and as long as conditions remain constant, then those relative amounts of products and reactants will also remain constant. However, systems very rarely remain constant for very long. And what we're going to be talking about today is what factors can affect the chemical equilibrium. All right. Now, these factors are often called stresses. Now, stress, the definition of a stress is a factor that can alter an equilibrium position. And if you remember, an equilibrium position is a particular set of equilibrium concentrations of all the reactants and all the products in a chemical system. Again, it's basically how much products you have versus how much reactants you have. Okay? And there is a principle, that's what it's called. It's basically a theory, but there is a principle known as Le Chatelier principle. And by the way, those of you guys that speak French, if I'm totally butchering that name, I apologize. It's the best I can do, okay? So Le Chatelier's principle basically states that when a chemical system that is at equilibrium is disturbed by a quote-unquote stress, the system will respond in order to relieve that stress. It's kind of like if you were standing and standing on one foot and you're all balanced, right? And then someone comes over and pushes you. Well, you're not going to just immediately fall over. You're going to like shift your weight or do whatever in order to avoid falling over. That's what a chemical system does. It shifts in order to avoid falling over, as it were, but it shifts to accommodate that stress and reestablish its balance. Now, when conditions change, then either the reactants or the products are what are known as favored. Now, when a side is favored, that means that whichever side is favored or whichever direction is favored, that reaction rate speeds up, all right, for a little while. And as it speeds up, it produces more of either the reactant or product. So if the forward reaction is favored, that means that you end up with more product. If the reverse reaction is favored, that means you end up with more reactant. All right. And it does this until the stress is relieved and it reestablishes equilibrium, until the reaction rates are once again equal to each other. All right. So the side that is favored increases in concentration while the non-favored side decreases in concentration. So if you have a favoring the products increase in concentration, but the reactants decrease in concentration. Now, what are the different stresses that shift equilibrium? Well, first of all, they are basically the same factors that affect reaction rates. And one of the main ones is concentration. Now, to help illustrate this concept, I have here a little device that I created to basically illustrate the effect that concentration has on reaction rates. Let's say this side represents the reaction rate, the concentration of the reactants, or basically the amount of reactants that we're going to start off with. So I'm going to blow this side up. All right. And then this is before the reaction begins, okay? And we have a certain amount of reactant and no amount of product. When I turn this knob, it's going to be like the reaction is going to shift to equilibrium. All right, you guys ready? Here we go. Boom. Now, This has shifted to equilibrium, and we have a certain amount of reactant and a certain amount of product. This is in equilibrium. The air from here is going as fast that direction to here as this is going to here. Once again, hopefully this illustrates the fact that the relative amounts of reactants and products do not have to be the same or equal to each other when they're at equilibrium, only the reaction rates. All right, so, nope. Let's, all right, so anyways, so this is at equilibrium. Now, the concept is if we were to add more to one side or another, then that side would be having more reactants, and we know that increasing concentration speeds up a chemical reaction, right? So if I were to add to a side, it should favor the other direction. So let's try that out. I'm going to shut this off. I'm going to add to this side. And let's see what happens when I open this up. And I don't know if you heard it, but it went shh. A little bit of this went over to that side. Okay. Let me set this up again. Now, what if I were to decrease this side? If I go and let some out, which direction do you think it's going to go? Well, it's going to go to fill up the void that I left. Since the concentration on this side decreased, it's not going to go that direction as fast. So it should go this direction. And let's see if it does. And it did. I don't know if you noticed that. This got smaller, this got larger. And then it reestablished equilibrium. All right? So the basic concept is this. When a reactant or product is added, the system shifts away from that added component. If you add to one side, it's going to shift over to the other side until it's balanced again. And if you remove from a side, it's going to shift towards the side that you removed the component until it's balanced again. Okay? It's kind of like, imagine if you have a seesaw and you have a bunch of weights on it, all right, and they start off being equal. If you were to take and add more weights to one side, all right, boom, you add more weights to one side. In order to equal and balance that out, we would have to take some of those weights from that side that you just added and shift them over to the other side for it to balance out again. So you add to a side, it favors the other direction, and you're going to end up getting more of the other side. Same thing is if you have this balance and you take away from a side, all right? In order to get that seesaw balanced again, we're going to have to take some from this side, put it over, all right? And it's going to balance out again. So you take away from a side, it favors the other side. You add to a side, it's going to favor that same side. Now, something related to this is the concept known as the common ion effect. Now, this is the reduction in the solubility of an ionic compound by the addition of a soluble compound that provides an ion in common with it. Now, what this basically means, it sounds complicated, but it's really not. If you have an equilibrium system where you have a solid that is in equilibrium with its aqueous form, all right? In other words, a saturated solution. And you take that solid, all right, and it's dissolving just as fast as the aqueous form is coming out or precipitating out of solution. So it's dissolving and it's precipitating, and you end up with what is known as a saturated solution. Again, it's kind of like if you add too much sugar to a bowl of cereal. You have that sugar that's on the bottom that's undissolved. Well, technically, it is dissolving and it's precipitating out of solution at the same speed. Now, what the common ion effect says is, well, what if I add another solution or another solid to that equilibrium? And that solid, one of the ions that it produces is the same as one of the ions in the dissolved substance, okay? Then that's like adding that ion to that side, and it will shift towards the other side, which is the solid, okay? Now, to help illustrate this, I think a little visual is needed. So let's say I have a solid, all right, and it is in equilibrium with its ions. Its positive ion and its negative ion. And these guys are in aqueous solution. All right. So solid is in equilibrium with its ions, both positive and negative ions. Now, let's say you have another solid that you put in there. All right. We'll do this as a different color solid. And it dissolves and it forms a positive ion and a negative ion. All right. So like you put sodium chloride in water, it breaks apart into sodium ions and chloride ions, okay, the positive and the negative. Now, if let's say this ion is the same ion as was here. These two happen to be the same ion. It's an ion that they have in common. All right? It's an ion that they have in common. Then it would cause, since you're adding more of this product, it's going to cause this equilibrium system to shift back towards this solid. And you would end up with more of the solid. In other words, it reduces its solubility. That's all that the common ion effect is, okay? It's a way of shifting an equilibrium by adding, in this case, a product. And the way you add it is by adding an ion that they both have in common, all right? So adding the common ion will shift the solubility back towards the left, favoring the reactant. Now, here's an example of stresses, of adding adding a reactant. So let's say you have a system here where you have this chemical reaction in equilibrium, where you have nitrogen with hydrogen in equilibrium with ammonia, and they're all gases. So if you were to go and add more nitrogen in, what would happen? All right, the nitrogen are these big double blue ones right here. If you added more nitrogen, well, that's adding a reactant, and that would cause it to shift towards the product, and you would end up with more of the ammonia, which are these guys like this guy right here. If you notice, there's only one here, but when you added more nitrogen, boom, you end up with two ammonias, one on the bottom and one right here. So it increases the concentration of ammonia, but also notice what happens to the concentration of the hydrogen. Here we had 1, 2, 3, 4, 5 hydrogens, all right? And then when we added the nitrogen, actually 6, we added the nitrogen, boom, it used up some of the hydrogen, and now we have less hydrogen. Now there's only 3 instead of 6. So it went in this direction, it used up some of this, and you ended up more of the product. Another example is when you change the volume or pressure. Now remember, when you're dealing with a gas, gases can be compressed, all right? So if you compress a gas, that increases its concentration. And if its concentration goes up, remember, it will favor the other side. So increasing the pressure on a side will favor usually the other side if they're all gases. But the basic concept is this. Decreasing the volume or increasing the pressure, same thing, favors the side with fewer number of gas particles. All right. For example, if you look at that same chemical reaction, you have on the left, on the reactant side, you have one nitrogen, that's a gas, and 3 hydrogens. So you add it up, you got a total of 4 gas particles. 1 nitrogen, 3 hydrogens. On the product side, those are all gas, but you have 2 of them. When you look at the coefficient, you have 2 ammonia. All right, ammonias. So you have 2 gas particles there. So you have 4 on one side, and you got 2 on the other. Let's do it this way. You got 4 on one side, 2 on the other. Now, if we increase the overall pressure of the system, it's going to favor the side that has fewer gas particles. Remember, gas particles take up a large amount of volume. So if you squeeze it down, it's going to favor the side with fewer, so it's going to favor the ammonia. All right? And that's what's going to happen here. Decreasing the volume favors the product, since the product has only 2 gas particles, while the reactants have 4 gas particles. Another example is here. Here we have calcium carbonate, which is a solid, and it's in equilibrium with calcium oxide, which is a solid, and carbon dioxide, which is a gas. So in this case, the reactants have 0 gas particles, whereas the product have 1 gas particle. All right? And if we increase the pressure, it's going to favor the side with fewer gas particles. 0 is less than 1. So in this case, it's going to go back and favor the reactants. All right? And keep in mind, if you have an equal number of gas particles, 2 and 2 or 4 and 4, then increasing the pressure or decreasing volume does not change the equilibrium. If they're equal or you don't have any gases at all, it does nothing. All right? So, next, the effect of a change in temperature. Now, temperature, as you remember, is one of those main things that changes reaction rates, all right? The higher the temperature, usually, it's going to favor and cause a reaction to speed up. But what happens when you have 2 reactions going in both directions? Theoretically, both are going to speed up, right? But if you remember from one of our previous assignments, if one direction is endothermic, the other direction has to be exothermic, right? Well, endothermic means that you're adding heat to that reaction overall. Remember, all reactions, you add a little bit of heat in for the activation energy. But in endothermic reactions, you add more heat than comes out. So overall, you're adding heat energy. Basically, when you increase the temperature of an equilibrium system, it favors the direction that is endothermic. You add more heat, that means more energy goes in, and the endothermic direction will be favored. But it won't favor the exothermic. So you got to figure out which side is endothermic and which side is exothermic. All right? So if you have, if you know that information right off, because of the whole negative, you might say that the negative side is the forward reaction is endothermic, and then the temperature goes up, you know the forward reaction will be favored. But what if you have just a chemical equation? Well, remember, chemical equations often have heat in them. So like in this equilibrium, heat, you notice, and it might be heat or it might be written as a certain number of kilojoules or something like that. If it's part of the chemical reaction, then it's going to either be a reactant or a product. If it is on the reactant side, that means the forward reaction is endothermic, because you got to put heat into it for it to go. If, however, this was on the product side, that means heat is being produced. That's an exothermic reaction. That would mean the forward reaction would be exothermic. And then if the temperature goes up, it would favor the reverse reaction. All right? Just to, so let's say instead of on that side, you saw the heat on the product side, heat's over on the product side, then increasing the temperature would favor the other side. All right? So exothermic reactions produces heat. Heat is a product. Adding energy shifts the equilibrium to the left. All right? So in this case, it's going to shift it left away from the heat term towards towards the reactant. If, however, it's an endothermic, in other words, it was on this side like I had originally, then it absorbs heat, the heat is a reactant, and it shifts to the right away from the heat term. And that, basically, is equilibrium, or the Le Chatelier's principle. And we're going to have some, I'm going to help you out, give you guys some sample questions on that. And basically, the skill that I want you to be able to have is if you see an equilibrium system and I tell you a particular stress, you need to be able to predict which direction is it going to favor. And that's where practice comes in. And if you need help, please come to tutorial. Thank you.